In the realm of explainable AI, SHAP scores are a widely used method for feature attribution. However, recent studies have identified limitations with their use, such as assigning misleading importance to features. This paper argues that these shortcomings can be attributed to the characteristic functions employed in earlier works. It proposes novel characteristic functions that respect fundamental properties and corrects some or all of the identified shortcomings. The paper also analyzes the impact of these new functions on the computational complexity of computing SHAP scores. The paper introduces a classifier M as a tuple, K, kappa, where F denotes the set of features, K represents the set of classes, and kappa is a non-constant classification function mapping feature space F into the set of classes K. The classifier can be Boolean, multivalued, or discrete. A deterministic decomposable Boolean circuit, DDBC, is defined, which generalizes deterministic decomposable negation normal form, DDNNF, circuits and allows for multivalued discrete inputs. The paper defines a function upsilon that represents sets of points in feature space consistent with some other point in feature space with respect to the features dictated by a set of features. It also assumes a uniform probability distribution on each feature, with all features being independent, and calculates the probability of an arbitrary point in feature space as p, x, equals 1, pi I element of f, d. The paper's key contribution lies in identifying essential properties that characteristic functions should exhibit in the context of XAI, proposing novel characteristic functions that respect these properties, and analyzing the impact of these functions on the computational complexity of computing SHAP scores. This work aims to provide a foundation for correcting SHAP scores and ensuring their safe use for feature attribution in XAI, while offering strong guarantees regarding known shortcomings. The paper discusses the limitations of SHAP scores, a widely used technique for explaining machine learning models. It presents two examples of classifiers where SHAP scores can mislead about the importance of features. In the first example, a decision tree classifier is used with a target instance 1, 1, 1, 1, 1. The computed SHAP scores indicate that feature 4 has the largest absolute SHAP score, despite feature 1 being the only feature that influences the prediction. In the second example, a simpler classifier is devised, and it is shown that SHAP scores can be misleading for both relevant and irrelevant features. The paper also highlights that the use of baselines can reveal similar limitations. In this paper, the authors address issues with the existing SHAP scores, which are used to measure feature importance in machine learning models. They propose new characteristic functions that respect certain properties, such as weak and strong class independence, compliance with feature, IR, relevancy, and numerical neutrality. The proposed functions include the similarity function, AXP-based, CXP-based, and numerical characteristic functions, denoted as upsilon s, upsilon a, upsilon c, and upsilon n, respectively. These functions are designed to eliminate misleading information about relative feature importance and can be used in settings where classes are not ordinal. The authors also provide basic attributes of these new characteristic functions, including their relationships and the complexity of computing SHAP scores. They prove which of the proposed properties are respected by each characteristic function and discuss the implications for feature importance measurement. This paper presents a novel approach to addressing the issues with SHAP scores, which have been observed in earlier studies. It introduces characteristic functions that respect numerical neutrality and guarantee strong class independence, thereby preventing misleading information. The proposed characteristic functions are based on similarity functions and can be used to correct SHAP scores. The paper also explores the computational complexity of computing SHAP scores, showing that for Boolean classifiers, the computation is intractable. However, for non-Boolean classifiers, the computation becomes n-fard. The paper demonstrates the effectiveness of the new characteristic functions by comparing them with SHAP scores obtained from a decision tree classifier. The results show that the new characteristic function enables obtaining SHAP scores that are not misleading. Furthermore, experimental results indicate that the use of the new characteristic function prevents the observation of issue I8, as proposed in earlier work. The paper concludes by emphasizing the importance of addressing these issues with SHAP scores, as they can lead to incorrect feature importance rankings. It suggests that the proposed characteristic functions may serve as a solution to this problem, and proposes further research into whether the use of these functions prevents more flexible variants of issue I8 from being observed. Here is a combined summary of pages 9 and 10 of the research paper. The paper addresses the issue of correcting SHAP scores, which have been found to exhibit problems due to the characteristic functions used in earlier work. To resolve this, the authors propose several properties that characteristic functions must respect in order to compute SHAP scores that do not exhibit these issues. The complexity of the proposed characteristic functions is argued to be as hard to compute as those used in earlier works studying the complexity of SHAP scores. The authors also propose simple modifications to the SHAP tool to obtain SHAP scores that respect some of the proposed properties. The paper presents a comprehensive review of the literature on SHAP scores, feature attribution, and explainability in machine learning. The authors cite numerous papers on the topic, including works on the tractability of SHAP explanations, axiomatic aggregations of abductive explanations, and the inadequacy of SHAP values for explainability. The authors highlight the importance of rigorous interpretations of feature attribution and the need for formalizations of feature attribution. They also discuss the limitations of SHAP values for explainability and the need for alternative approaches. The paper concludes by highlighting the potential societal consequences of the work, although none are specifically highlighted. The authors provide a comprehensive list of references, including papers on SHAP scores, feature attribution, and explainability in machine learning. Overall, the paper presents a thorough analysis of the limitations of SHAP scores and proposes a framework for correcting them. The authors provide a comprehensive review of the literature on the topic and highlight the need for rigorous interpretations of feature attribution. Here is the combined summary. Correcting SHAP scores involves analyzing the characteristic functions =A, =C, and =n, which are used to compute SHAP scores SCA, SCC, and SCN, respectively. Proposition 4.1 states that a strongly class-independent characteristic function is also weakly class-independent. Proposition 5.1 proves that SCA, I, is greater than or equal to 0, SCC, I, is greater than or equal to 0, and SCN, I, is less than or equal to 0 for all I in F. Proposition 5.3 shows that SCA, I, equals SCN, I, and SCA, I, equals SCC, I. For all I in F. Proposition 5.4 proves that the characteristic functions t, t element of S, A, C, N, respect strong class independence. Proposition 5.5 states that for t element of A, C, N, feature I is irrelevant if and only if SCT, I, equals 0, implying that SCT does not mislead. Computing SHAP scores is hard for Boolean classifiers in CNF or DNF, as shown in Proposition 6.2. Moreover, computing SHAP scores SCT, t element of A, C, N, is hard for DDNNF and DDBC classifiers, as proven in Proposition 6.3. The limitations of SHAP scores based on baselines are also discussed. Specifically, the B-SHAP characteristic function B is analyzed, and it is proven that B-SHAP is only well-defined if all domains are Boolean and if the baseline W equals not V, proposition B1. Additionally, B misleads, as shown in proposition B.2. Overall, this research provides a comprehensive analysis of SHAP scores and their limitations, highlighting the importance of careful consideration when using these scores to explain machine learning models. On correcting SHAP scores, the set of AXPs is determined to be 1, and the kernel function kappa x1, x2 is evaluated as 1 if x1 equals 1. However, the computation of SCB yields SCB 1 equals 0 and SCB 2 equals 1, which is misleading. To rectify this, the SHAP scores are recalculated as follows. The B values are computed as B, empty set, equals kappa, 0, 0, equals 0, B, 1, equals kappa, 1, 0, equals 1, B, 2, equals kappa, 0, 1, equals 2, and B, 1, 2 equals kappa 1, 1 equals 1. Subsequently, the increment b values are calculated as increment b 1 empty set equals upsilon b 1 upsilon b empty set equals 1 increment b 1 2 equals upsilon b 1 2 upsilon b 2 equals 1 increment b 2 empty set equals upsilon b 2 upsilon b empty set equals 2 and increment b 2 1 equals upsilon b 1 2 upsilon b 1 equals 0. Finally, the corrected SHAP scores SCB are computed as SCB 1 equals increment b 1 2 plus increment b 1 empty set 2 equals 0 and SCB 2 equals increment b 2 1 plus increment b 2 empty set 2 equals 1. The corrected SHAP scores demonstrate that the initial computation was indeed misleading. The recalculated scores accurately reflect the contribution of each feature to the model's output. This correction is crucial in ensuring the reliability of SHAP scores in explaining the model's behavior. The methodology employed in this correction involves a meticulous evaluation of the kernel function and the upsilon b values, followed by the computation of the increment b values and the corrected SHAP scores. This approach highlights the importance of careful consideration in computing SHAP scores to avoid misleading results.